what is the voltage, what for a capacitor or an inductor? What formulas do you know for those things? So, what is the voltage across a capacitor? Or what's the current across a capacitor?
C dV dt.
C dV dt. And what is the voltage across an inductor?
It's L
Di dt. L di dt. So if I look at a circuit that looks like this, and I try to do a KVL around it. So I've got some voltage here, a voltage source here. The voltage across the capacitor, I can call that, right now I'll call it VC. And then the voltage across the resistor would be I times R. And the voltage across the capacitor is L di dt. And so everything here has the same current because they're all in series. And so if I take the derivative of this I right here, di dt, I get that is C dVc dt, or d squared, the second derivative of dVc dt. And so then I can rewrite this voltage across the inductor as L times C d squared Vc dt squared. And then if I do my KVL, I get minus Vs plus Vc plus I is C dV dt, C dV dt times R, plus LC d squared Vc dt squared, all equals 0, and I get a second order differential equation. So you learned in your differential equations class different ways to solve this. And using those just regular techniques, you came up with, or you can solve these equations if this voltage is something nice, if this voltage is not a function of t, or even if it is a function of t, maybe some ways to do it. And then if it falls into special categories, you can use these sets of equations that were given to you.
Among other things.
Where is it? Where is it? There we go. Okay. So you have these sets of equations, and I believe I've worked a couple problems like this, worked one or two of them with you, and I have others that are online using these. And these are, you get your circuits in this form, or you get your circuit in this form, and then you just find out what kind it is, and you just kind of plug and chug and find the answers. And that is all fine, as long as you can get it to look like this series RLC or a parallel RLC, and you notice there's no sources in this, or your input is a DC circuit with a switch action at t equals 0. So it's just a DC. But what if you had a function? What if the thing driving it was some sort of function? Well, in that case, you need to use a different technique to solve that differential equation. And it turns out the one that is most convenient for solving these kinds of differential equations is by putting them in using a Laplace transformation. So what is a Laplace transformation? So a Laplace transformation used to be in chapter 6. Is it in 12 or 14 now? I guess it was in 12.
Is what you have more updated than what?
Mine is about the same as what the is used for the Xi books, but I think that one is edition 4, this is edition 3, and I learned from edition 2, so nothing is where I think it's going to be when I go to look at this. Okay, so what the Laplace transform is right here. So this is the definition of a Laplace transform. In this class, you won't have to use the definition, but what it does, and you'll notice it has it in this bold, so that's how you know you've got a Laplace transform. You come up with a new function, and the new function uses the variable s. And you're going to see this again when you take controls. Anytime you see the s variable, you know you're working in they just call it the s domain, and the s domain means that you've transformed everything using Laplace transforms. So it's like, I think my description earlier described it pretty well. It's just you're taking your entire problem, doing something to it that preserves the relationships between them but makes your problem easier to solve. You solve it, and then you bring it back.
Kind of like the substituting U, like U and V.
Exactly. Yeah, that's a good analogy. Doing the U substitution is an excellent analogy. All the relationships are still there. You just made it so that now you can factor it, or now you can integrate it. And when I write this, I use this little L to indicate that I'm taking the Laplace transform. And then I use curly brackets. So the Laplace transform of f of t would give me a new function in s instead of t. And what that function is, if you look at how this is defined, it's defined as you take your function, you multiply it times e to the minus st. So s in this integral is not the variable. You're integrating with respect to t, but you've got that s thrown in there. So like, for instance, if I wanted to take the integral, so first of all, you need to know do y'all know, you know the unit step function, you don't know the delta function. Okay, let's think about what would the integral of the unit step function be with respect to t. So 0 minus, starting at 0 minus, not really that important here, just means that I'm including 0. What is the unit step function?
But t greater than 0 is 1. No.
Yep, that's it. Yep, t greater than 0, it's 1. Okay, so geometrically, what is an integral?
Area.
Area. So what would the integral from 0 to 1 of u of t dt be? 1. What would the integral from 0 to 2 of u dt be?
2.
How about the integral from 0 to 65 of u of t dt?
65.
All right, so now if I take the integral just in general from 0 to t of u of tau d tau, and I'm just using a different variable here just so that I don't have that integral up there, what I'm going to get is t. And so if I take the integral from 0 to infinity of the unit step function e to the minus s of t dt, what I get is I thought I'd be able to do this quickly, and I'm not. I can do it, but it's not going to be worth the time to do it. But if you go back and look at your tables, you have given to you, so you don't ever have to do that because you will have this table. You will have the table of the Laplace transforms. And if you look right here, this is the one that I was about to do and then said, no, it's not worth the time to do it. The Laplace transform of the unit step function ends up being 1 over s. And so this first column has a list of a bunch of different functions. The second column says what that becomes after you take the Laplace transform of it. And so you use this to transform your circuit into the S domain, and then after you've worked your problem, you transform it back into the time domain going the other direction. But the reason Laplace transforms are so useful is because of these properties right here. When you take the Laplace transform of a derivative, you get back s f of s that is not a derivative. So if I have a function that looks like y double prime plus y prime plus y equals 0, or if I have an equation that looks like that, and I apply the Laplace transform to everything on that equation, what I get back is s squared, a new function y, minus s little y of 0 minus y prime of 0, that all of that is the second derivative, plus the first derivative is s y minus y of 0, and then the Laplace transform of little y is capital Y equals 0. Now I have an equation. If you look at my second equation, there are no derivatives in it. It's not a differential equation anymore. It's just an algebraic equation. And algebraic equations are a lot easier to solve. So when you take the Laplace transform of these circuit elements, you get that you get this result. So there's a lot of theory in here that's real fun, but okay, yeah, you get this result that
Remember, she said the resistors don't change.
resistors are lovely. In all of the domains you're going to be working with, resistors just stay R. So resistors are nice. Resistors don't change. So inductors become SL, and then what I always forget is if you remember when I was doing my demonstration just a minute ago, the Laplace transform of the first derivative turned out to be sy minus f of 0. It has that extra thing in it, so you have to have boundary conditions. If you don't have boundary conditions, then Laplace transforms don't help you much. But if you know what the conditions are at time equals 0, which y'all have been practicing on, then you'll add to this SL, you'll add either a little voltage source that has the value of the current at time equals 0 times the inductance, or you'll add a current source in parallel. And so you do have to know what the current is at time t equals 0. And this same with the capacitor. I almost always use this first column just because I like voltage sources and not current sources. So if you take a capacitor turns into 1 over SC. So if I had a circuit that looked like this, and I wanted to find something out about it, like determine the capacitor response IC of T in this circuit. Okay. Do I have numbers? Yes. So we're going to walk through this one and see how it all comes together. So this is an actual like problem example. Okay. So the first thing that we need to do is to transform everything into the S domain. So
Is this how they got the equations for the parallel or series RLC circuits?
you mean with all those alphas and omegas? Mm-hmm. No, those you just solve them. Oh. So the first thing that I want to do is, and I can't use those equations for this because this voltage is not uniform. It has a value, or the current is not uniform. It has a value of 6 amps at between 0 and 1, and 0 everywhere else. So it's not just like an on-off. It's kind of an on-off. It's an on. It's off and then it's on and then it's off again. So that's what makes it different. Let me see. I want to do it the same way they do it so I can check my work. They're using to keep it in current. Okay. So the first thing I want to do is rewrite this current source as a function. And so it would be the unit step function times 6, because that gets me, it's 0 until I get to 0, and then it becomes 6. And then I need to subtract out the unit step function t minus 1 times 6. And so that will get me that one. I don't think you're ever going to have to do this. You would just you'll probably just have a number there. You won't ever have to do that kind of transformation. Okay, so now I need to put everything into the S domain. So the nice thing is in the S domain, everything acts like a resistor. You don't have to say, well, what do I do with capacitors? What do I do with inductors? They all act like resistors. So the capacitor becomes 1 over SC. The inductor becomes SL. The resistor remains R. Now I need to take the Laplace transform of U of t times 6 minus U of t minus 1 times 6. Well, I just showed you in the table, so we had it in our heads, or you might remember the Laplace transform of the unit step function was 1 over s. So this first one becomes 6 over s minus, and then if we go back and look at our table, let's remember what page it's on in case I have to come back to it. Or I can just copy the table.
I thought you did.
I copied one table. There's like 3 tables we need. Is it this one? It is this one. This is usually not the one you need. Usually you need the other one. But this one has the time shift. So the Laplace transform of f of t minus capital T times u of t minus capital T equals e to the minus ts times the Laplace transform of s. And so what I'm trying to take the Laplace transform of is u of t minus 1. So my function, my capital F, is 1 times u of t minus 1. And so F is 1 and capital T is also 1. So the Laplace transform is e to the minus s, and this capital F means the Laplace transform of little f and little f was the unit step function. So that's e to the minus s times 1 over s, and then I also had a 6 in there. So this is going to be six e to the minus s times 1 over s. All right, so now okay, so now looking at, let me do that.
It was 6s minus 6
E to the s times 1 over s. This is not, I'll set it up and then we're not going to solve it from there because it won't be helpful to solve it from here because you're not going to have any that hard. So let's take a look at doing a nodal analysis from this right here. So the voltage right there is capital V because we're all in the S domain, so imagine it's bold. And so V is going to equal minus is plus v over r plus v over SL plus v over 1 over SC. That's not what v equals, that's at node v. At node v, this all equals 0. So we would have v over r plus v over SL plus v over 1 over SC equals is. So then you can factor out a v, and we'd have 1 over whatever r was. I'll leave it just r for now, because you're going to have to do a similar thing most of the time with these problems, plus v, oh wait, no v anymore, 1 over SL plus 1 over SC equals is. And then you would divide both sides by this thing that's in parentheses. So you would get v equals is over 1 over r plus 1 over SL plus 1 over SC. I'm sorry, 1 over 1 over 1 over 1 over SC. And then typically what you do at this point is you multiply through by something that will help us get rid of the s's in the denominators. So you multiply through by s over s. And then you would get is over s over r plus 1 over L plus s squared s squared c equals 0. And at this point, what you have is something that has a quadratic in the denominator. 1 over r, 1 over L, those are just numbers. If you are going to then try to figure out, take this back into the time domain, you then have to take the inverse Laplace transform. And this is why you do partial fraction decomposition, because when you have something that looks like, let's say it looked like this, 1 over s squared plus 6s plus 5s plus 5s plus 6, and you go to your Laplace transform table to try to get the inverse Laplace transform of that, and you look at your table, you see that in this table there's nothing that looks like that. There's nothing that looks like just a plain old quadratic. But you do have something that looks like just 1 over s plus a. So if I can rewrite this into sums of individual things, then I can get that, I can take the inverse Laplace transform of it. So here, let's, okay, so what I'm going to do now is, now I've tried to give you a very quick, here's why. So what I've now said, I've now done all the here's why. Now we're going to just like put numbers in and actually do, we can either do the partial fraction decomposition of this, which is easy, or we can start with a fresh problem that is going to give us something useful that would be like what you might see on the test.
Okay,
So,
useful sounds good.
okay, let me get a good one. And what do we have? About 15 minutes should be good. Do either of you have a lab or anything that starts at 11:30?
I have a class at 11:30.
Okay, I'll try to get through the good stuff in 3 minutes. I'll see what I can do. Okay, let's get, and if I recall, all these were hard. Let's, I should have one on a worksheet. Just have to find it. I'm not gonna find it in time.
Pressure.
Circuits 1, worksheet 14, solutions. Looks promising. These are gonna be hard. Circuits 1, worksheet 10.
Plus test one.
Yeah, that's probably not it. Let's see. This, I just was doing it, but not in a circuit.
You have like a treasure trove.
I've got, yeah, but unfortunately it's not organized very well. This ought to have something good in it. Just pick one and do it as a Laplace transform. Yeah, I'm not going to get to it in time for you, but I will. That's the one I was just about to do. Very similar. All of the ones in this book are so hard. I know I have one that just works out really nicely if I can find it. Worksheet 15, worksheet 17.
That thing that pops up first always just like, oh my gosh.
What's that?
That.
Oh, yeah. I'm just gonna do this one. It's not, so. I know it works. Where did it go? Okay, so we know. Why is it not pasting?
Because it knows you have a limited time.
Right. That's exactly why. All right. So, we know that V naught is 12. We do need to know for this, when we transform it into the S domain, we do have to know if there was any current, current through the inductor or voltage across the capacitor at time t equals 0. So at time t equals 0, let's look at what this would have looked like before the switch action and see if there was a voltage across the capacitor or current through the inductor. So was there any current through the inductor?
At t equals 0 minus?
At t equals 0 minus.
No.
So at t equals 0 minus, IL is 0. What about VC of 0?
The voltage division on the 1.2.
That's right. It's in parallel with the 1.2, so it's going to have the same voltage as the 1.2. So 12 times 1.2 over 1.6, 12 times 3/4, which is 9. So then if we look at how capacitors and inductors change in the S domain, we had that where'd I go with my book? We have that capacitors become 1 over SC and inductors become SL, but capacitors get added with them a voltage source that has the orientation, the polarity of the voltage source looks like the way it is there. So if we go back and look at ours, we're saying the current through the capacitor would be coming from the top, and if we compare that to our picture here, the current coming from the top, our polarity is going to have the positive on top. So it'll be 1 over SC and then 9 over S. Yeah, I understand, and I'll have this, this will be recorded so you can come and look at it.
Thank you.
You're welcome. Okay, so now we see that if I've transformed everything to the S domain, it now looks like this, where L was 0.1 and C was also 0.1. So this is 0.1 S, and this is 1 over 0.1 S.
Okay.
So now, if I do KVL, I would get 1.2 I plus 0.1 S I plus 10 over S I plus 9 over S equals 0. So I'll pause for a second and make sure that makes sense.
So that SL just acts like a,
They all act like resistors. And so once you put them in the S domain, everything acts like a resistor.
so
It is. It's bizarre.
okay.
Okay, so now Word is letting me paste, so just use Word. All right, so now the thing that I'm going to solve for is I, and so I need to take anything that doesn't have an I to the other side, and I'll factor out an I of what's left over here. And now I can divide both sides by the thing in parentheses. And then I'm going to multiply through the inside this parentheses. I'm going to multiply through by no, I'm going to multiply my fraction. Nope, I'm just going to multiply this s that's already on the outside through. I was like looking for the best way of getting the s out of the denominator. It's like, oh look, I have a handy one right there. 1.2s plus 0.1 s squared plus 10. Now I need to get this in correct quadratic form, either to factor it or to do something else with it, and I need to get the s squared in front, and I need it to have a coefficient of 1. So I'm going to factor out a 0.1 from everything. So divide everything by 0.1. And this does not factor. So I don't believe it does. 10 and 10 doesn't work. 20 and 4 does not work.
Not in a nice way.
Yeah. So your Dr. Manal will not give one like this on the test. You will have to do them at some point in your future. And different people do them different ways. I think the best thing to do is to pretend that it worked out into something that factored, because that would be what she would give you. So let's pretend that what we got instead was
Do you have to do like the
I'm going to do the partial fractions.
okay.
I don't know if that was what your question was.
So if you can't break it out into,
Oh, if you can't factor it, what you do is, so the way Mr. Rabelais taught it was to factor it under the complex numbers, and just factor it under the complex numbers, and then use the inverse Laplace transforms. The way they teach it in the differential equations class here is to do it using by completing the square. So half of 12 is 6 squared is 36. And then if I subtract 36 from 100, I get 64. So this is now, those things are still equal. But now I can write this as 0.1 s plus 0.1 s plus 6 squared plus 8 squared. And then that is in the table. So it's not bad once you see that, and you go to the table, and it's almost in the table. I need to have a plus 6 on the top. Do you want me to continue working this one, or work one like what you're going to have on the test? Or do both? Okay.
I want to see this one.
Sure. Okay, so let's finish it.
This will make the other ones easy.
Well, except this one doesn't have a partial fractions. So,
So it's not going to be easier.
no, it's just you haven't practiced. It's just something we haven't practiced yet. Let me see if by any chance OneNote will let me paste now. Yeah, no. Oh, yeah. Oh, because I was using Word. It's like, oh, yeah, okay, all right. All right. So now, oh, but it's not going to let me get more space on the page. And now it's not going to repaste it. And now it's gone. Okay, just have to, we can scroll this way. We just can't scroll down. Our computer's awesome. Okay, so now I have minus 9 over 0.1 times s plus 6 squared plus 8 squared. And in my Laplace transform table, what I have is, when I have in the denominator s plus a squared plus omega squared, and in the top I don't have an s, I need the omega to be on top as well. So in order to take the inverse Laplace transform of this form. So the form that I need to get it into is this. Is that. I need it to look like that. And so this, my omega is 8, so I need to have an 8 on top. So I'm going to start just by bringing my negative 9 and 0.1 out in front, and that becomes a negative 90. And I have 1 over s plus 6 squared plus 8 squared. And now I need to get an 8 on top, so I can do that by multiplying by 8 over 8, but taking the bottom 8 and just giving it to the negative 90. So I have negative 90 over 8. I feel like I've made a number error somewhere, because everything feels correct about this problem except for that negative 90 over 8. It does not feel like the right answer. Where did that 0.1 come from? I'll never know.
Point one was
Factoring out from the denominator, and it came from the 0.1 from the inductor, which was 0.1 henries, so that all appears right. The 9 came from the, I think the reason why is most times when I work this problem, I forget about this part from the capacitor, where you have to add in the voltage, and so I'm used to working it without the 9, and then at the end trying to figure out why my answer is wrong, and then going back and realizing that I need to put this 9 in.
Oh.
So I think the reason that the number doesn't seem familiar is because I remembered the 9 this time. Okay, so now it is in the correct form because it is of the form omega over s plus a squared plus omega squared. So now I take the inverse Laplace transform. So I take the inverse Laplace transform of negative 90 over 8, which is negative 45 over 4, which is negative 10.25. Negative 10.25 of 8 over s plus 6 squared plus 8 squared. And the inverse Laplace transform of that, the number, a constant out in front, just stays there. So you would have negative 10.25 times e to the negative 6t sine 8t u of t, and that equals the current as a function of time. And then I'll do one complete example if you have time.
And you basically just plug that in.
I just plugged it in. So taking the inverse Laplace transform is, what that means is putting yours into the format of one of these in the table and then just figuring out what A and omega are and doing it. Okay, so do you have time for